let's start with realignment. Maybe let's just do one session. I think we can do this whole thing in one session. Or you don't feel like you need a break, right? It's not like we have J indices and omega J's and going from -1/2 to n+1 or something. It's pictures and some talk that one can listen to or not. So realignment then. Realignment, also known as motion correction, is something that is actually always done and is also sensible to do. So head motion is of course an issue because the scanner, when it images things, it assumes that the sample stays in the same position during the imaging process. Of course, if you have your brain in there, you do a couple of images over time, and then you move your head somewhere where in the data grid that the scanner puts a certain sample, the data will be completely different if you move your head out of this data grid. Of course, this is not what participants usually do. However, there's a little bit of movement even if you try to keep your head still. And especially at the edges of the brain, this actually makes big differences. So here you see the grade level values when things are like that. And then if you do a little bit of movement here in this direction, then you see that the data changes quite dramatically. So it goes from 119 here to 520. So motion affects the values that you get for your voxels. That's what this slide wants to say. The effect of head motion, which you then sometimes pick up using your regressors that pick up variance because they are themselves a variable. You can usually see that the head motion was not fully corrected by getting activations or voxel significances at the edge of the brain, because this is where the motion effects are most pronounced, as the previous slide had shown. So what can you do? The best thing about the whole thing is, of course, preventing head motion. Preventing head motion in the first place. So usually you put the participant into some cushions. What you can also, in this way I looked closer, use these, and I think this is actually one, use these vacuum-based cushions that where you can suck the air out once people are in there, and then they are kind of in the mold that is specific to the head, and then they really feel if they move. They are not the most comfortable ones, and especially if you have your head for a long time on a quite hard surface, it starts to hurt, because you compress the capillaries in your skin, and it actually gets quite uncomfortable at one point. You can use bite bars, but that's also not really done, and you can go to your favorite SM studio and be strapped onto a table and then look like that. Sorry. I just find this image funny. Nobody does this kind of thing, but this image is awesome. Yeah, every year the same joke. But at least it's on video now, so I don't have to make this joke here. So essentially you try to tell your participant that they shouldn't move, and why is actually he's even naked as it looks, right? So he doesn't it doesn't seem to wear anything. That's completely weird. Anyway, that's the prevention of head motion. So that's the most important thing. So tell your participant to not move their head, and also try, if you're a participant yourself, not to move your head. There is still residual motion, which you might be able to get this especially if you're dealing with kids. What one can do, and this is what's shown here, is using mock setups, specifically with specific participant groups like kids, to train them to stay still one can also do that. Usually the common participants are, of course, your fellow scan students. So there, also we don't have a mock scanner here, and you will not train them, but to encourage them to stay still. Even if they stay still, there's some residual motion also, for example, by the heartbeat, which pumps blood into the head, of course, and there's a little bit of movement also associated with that. So one needs to correct for that. And what is typically done in terms of correcting for head motion is that 6 parameters are estimated, namely parameters relating to translation in the X, Y, and Z direction. So if you move your head up, to the left, to the right, or back and forward. And so that would be 3 parameters, so X, Y, and Z translational movement, and rotation around the X, Y, and Z axis. So these are parameters, 6 parameters that are typically estimated. What of course doesn't play a role for head movement correction is the scaling. So the head of course doesn't get bigger or smaller by movement or any kind of sharing things. These kind of operations and estimation of the parameters, they are important for normalization that we will see later. So for correction of head movement, usually 3 translation parameters, Z, Y, and Z, Z, Y, X, Y, and Z, sorry, and rotation, 3 rotation parameters, X, Y, and Z are estimated. This shows then basically the logic of how this is done. So you have here the original time series in volumes, so these are not slices now, these are volumes. This is one slice of a given volume, and for each difference between 2 volumes, 6 parameters are estimated that relate to the translation and the rotation, and then these parameters are used and are applied to the original image sequence to reslice, that's the term there, to reslice or interpolate the raw image to obtain a movement or motion corrected volume. So how that then looks in more an applied setting is as follows. So if you run a realignment algorithm, what you have to specify is a reference image, and then the realignment algorithm estimates the translation and the rotation with respect to the reference image, which is usually just your first image. So you say this is my reference, and then the algorithm tries to estimate the translational and rotational parameters, and then you get, for example, if you do an SPM analysis in the end for here 3000 volumes, you get the parameters. So you see, for example, that there was quite some movement in the z-axis, and then here there was some jump in the z-axis where maybe the participant did something. However, this is not really much, this is in millimeters. Same for the rotation. The rotations around the x, y, and the x, y, and z axis, they have names. They're called pitch, yaw, and roll. You don't have to remember which one is which, because I don't remember which one is which. But yeah, so they these are the estimated parameters. These parameters then are applied during the reslicing, and this shows what the result is, for example, for translation. So before motion correction, so before essentially reslicing the images, these were the parameters. Then after motion correction, if you again try to estimate the parameters in terms of translation, they are much lower. So that means that the algorithm is at least self-coherent. So first it estimates this movement, then you reslice so that this movement shouldn't be there anymore, and then afterwards it doesn't measure that much movement anymore. And this is, I think, just the relative displacement, I think, between slices or so. Don't quite remember. The important thing is here that the translation is first strong, parameters are estimated parameters are used for reslicing or interpolating the raw data, and then afterwards it's better. Yeah, so that's motion correction.
I have a question. You said that the algorithm tries to estimate the parameters from one first image, so is that a static image or?
No, so what it cannot do it based on one image. So it does. It's always so you take the first image, and then the algorithm estimates how much the second image has changed if you assume a translation and a rotation, and what the parameters of this translation and rotation are. Yeah, so it tries to basically match two images. So it, let's say this is the original image, and then your next image is that. What the algorithm tries to do is try to use rotation and translation. So let's say it's like this. It tries to do a translation and a rotation so that they are aligned. And if, of course, you need, this is of course a technical algorithm, so you need some kind of loss function, and you try to get to this where you have minimal loss. And then you can try different translations and rotations to achieve that. Once you have achieved that, you of course know for the second one how you got there, and these are then the parameters. Yeah. And then you do it for the next slice, again with respect to the first one.
Okay, yeah. Yeah, but the parameters, I get them from the algorithm, but the algorithm needs the parameters, right?
So there you have to, this is, this is a little bit more going into the actual data analysis, but there are two steps. So one, this is why in SPM, for example, it's called estimate and reslice. So the algorithm, there are two algorithms. One algorithm estimates the parameters, and then you have the parameters and you can look at them, but the data is not corrected. And then there is an interpolation algorithm or an interpolation step where these parameters are used to resample the original data. Yeah. So the first algorithm doesn't need the parameters because it estimates them. The second algorithm, which is just an interpolation, needs the parameters, but it doesn't estimate them.
Okay.
Yeah? Estimate and reslice. Good. This shows that it works. And my favorite topic, smoothing. So maybe to come back, so the first thing that makes sense in terms of data preprocessing from my perspective is definitely quality assurance, to look at the raw images and then do realignment, because then you have, you do some motion correction, you get rid of some motion artifacts, and you have motion corrected your data. Often what is also used in kind of pre-processing, I think I usually do that after normalization, but it's here now before normalization, is spatial smoothing, which is just computing essentially weighted averages with then in this context called kernel function, which is just a Gaussian, which is then usually quantified in terms of its full width at half maximum, which is just a conversion of its standard deviation. So if you have a large standard deviation, you have a large full width at half maximum. So half maximum means that you are at the 1/2 between 0 and its maximum, and the question is what's the full width here. So that's the conversion formula between standard deviation and the full width half maximum, but this is how things are quantified for Gaussian spatial filters. Of course, the data we are dealing with is actually not one-dimensional, but two-dimensional if you do it slice-wise, but you actually do it volume-wise, so it's three-dimensional. So you need to, you basically use 2D Gaussians or 3D Gaussians, and you see the isocontours here. This is kind of the task to familiarize you a little bit with multivariate Gaussians, so look into that. There's a whole chapter in the PMFN on multivariate Gaussians. They are just extensions of the univariate thing to more than one dimension. If you apply these filters, so these basically you put a Gaussian here, compute the average and weighted average, and then you shift the filter window and compute an average, then what you can do with that is that you make the data smoother. So if you increase, and what this shows is if you increase the width of the filter, then for broader filter width, the data gets smoother. Yeah? So this is not smooth, this is a little bit smoother, 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 very smooth. Yeah? We discussed, I think, at one point here also this matched filter theorem. So the one reason why one wants to do smoothing is if one assumes that the activations in the brain actually look a little bit like what you see here. So these kind of subblobs in this, then of course this is not the right representation. You see that better here. That's one way how you can justify smoothing. You can also say well, this looks a little bit salt and pepper style. Nobody will believe me that here really something activated. Let's smooth it. Ah, yeah, now it looks nice. And then there's the story about random field theory and smoothing. The random field theory based p-values, just a second, the random field theory based p-values, they actually need a measure of smoothness. So they are the p-values that you assign to peaks depend on the smoothness of the data, which is estimated from the data, and have been shown in some Worsley publications from the 90s to do specifically good if there's a given smoothness. The whole random field theory business and p-values, that's a whole semester issue that we did last summer term. So there are videos online, there's a paper online. We will not go into the details there because that's a whole new mathematical framework. But you will sometimes find that people argue for smoothing in the context of random field theory based p-values. It's not quite correct, but sometimes it comes up. That was a question.
So this filter, I don't really get it. Isn't this full width half maximum always the same for a certain distribution? Because you're just aligning two. Maybe I didn't get it at all. But also
no, so that's a free parameter of your filter. So you should not think about these things here as distributions. They are just functions. For some reasons, and for good mathematical reasons, these functions are the Gaussian probability density functions, but they are not acting here as probability distributions. So they are not distributions. They are just kind of the kernels of the filter. So you weight the data that you have by these numbers, and then you can of course increase or decrease the full width half maximum, because this is a parameter of your filtering algorithm. And if you increase the full width half maximum, you get a broader filter kernel, and the result of applying this broader filter kernel to the data then looks that the result of the smoothing looks smoother.
I don't get it. I don't know, maybe.
So I think the reason is that you not quite know how filters work, and that you also not quite get what I mean when I say a weighted average. So let's do an example on the blackboard. So how this works is that you have a correlation. Okay. So how this works is that you have discrete data. How do we do it? So this is your data. Like this, and then you create in 1D here, then you create a filter that then is also of course discrete, and you apply this filter essentially for all data points. So you compute the weighted average. So what you get out is you multiply, so you do piecewise multiplication of these things, and then at this location you sum all over them. Yeah? So you essentially do a dot product. Now, if your filter is like this, essentially not much will happen, because this is multiplied with this is essentially large, and this is multiplied by this, and you allocate the average here, so it doesn't really have an influence. If you use a broad full width half maximum, so your filter looks something like this, then the data that you will put here has quite a contribution from this, so it gets smoother. So this has an influence of what you will plot here. Now, this is the first thing, and then you shift the filter window here and do the same thing. That's how filtering works.
Okay, so you apply a filter for every data point.
No, you shift the filter.
Okay, yeah. Okay, but for every data point.
Yeah.
Okay.
And that's just filtering. And then if you do this with a broader filter window, of course you will take more data from adjacent sites into the data point that you then allocate to a given site. And if you take, so you have a running average, and the running average just takes data from more sites. But this is filter theory.
So this width which you take is a kind of like the standard deviation of a certain kind of Gaussian.
It's just the width of the filter. It's just a parameter, and the standard deviation of the Gaussian you can convert based on this little formula there, this ln whatever. You can just convert into the full width of half maximum. If you want to prove for that, that's actually in the paper on random field theory.
Is it possible, for example, if you do, for example, apply the smoothing, and you can make your data not valid anymore, like if it's too much? I don't know, it's like with the sound when...
Yeah, so the thing is, there is... no. So all of this data preprocessing that we discussed here is things that you can do to data, and this is all data analysis, and there is essentially no wrong or right. What this is actually, this thing here is an example where this is from the Hütte, where it's discussed that of course it has an influence of what your results are. So for example, here the story is that if you smooth with a full width half maximum larger than 7 millimeter, then you only get activation here of one part of the striatum. Here, if you smooth with smaller than 6 millimeter, you get activity in both parts of the striatum and also some insular activity or whatever that is here. Thing is, this is all social convention. So you should smooth with, if you want to smooth data, and everybody smoothes data, you should smooth like your fellow colleagues smooth. Then everybody will say, that makes a lot of sense. And if you smooth completely different, then they will say, why? And then you need to argue why you did it differently. But this applies essentially to all of these pre-processing steps. This is all social convention. There is no right or wrong.
So, for example, here it just shows like the activation here is more strong, yes, like you're comparing.
Yeah, but of course you never.
If we lose this part, it doesn't like make any.
Yeah, I mean, so if you have the means to really, this is of course done from fMRI data. If you have the means to really compare this with some ground truth. So if you would assume, let's say, that you have simulated, that you have built a biological brain that you can fully control, and you can induce some neural activity, and the neurovascular coupling, everything is really built in biological tissue, and you have full control of it. And then you do the imaging, and you control that you do some activity only here, and with this smoothing you get this, and with this smoothing you get that. Then you could say, okay, this smoothing is right, because you know what the ground truth is. The problem is that, of course, no one knows what the ground truth is, and it's also not, we cannot easily create it, because you would really have to build a biological brain that you have full control over. As long as this is not done, you don't know what's right. You can, of course, relate this, and this is of course the story here, maybe relate this to some other findings. So if there's converging evidence that for the contrast that was done here, only this brain region lights up. And this was shown in 100 studies. And you believe these studies really, really, really strongly. And then you find on this smoothing that the whole brain lights up. Then you can say, okay, this must be an artifact. I believe this more.
I have a question regarding the function, the Gaussian function, because you previously said that it's not acting as a probability distribution, but just a function. And I've read that you do smoothing in order to enhance your signal-to-noise ratio, and that, well, that's what I've read.
Yeah.
I just wanted to check if that's true, like that you do that to enhance the signal-to-noise ratio, and that they assume that the noise is kind of randomly distributed, so like over the brain, but the signal is not. Like if you want to measure activation, the signal, of course, is not random. So, well, what I was thinking is that this is kind of a distribution to kind of apply a kernel to equal out all the noise.
Yes, but here is just a weighting function, and if you're talking about spatial noise, then you of course would need to you can talk about spatial noise, and you can also define spatial covariance matrices if you do spatial Gaussian noise. However, in the filter business, it has nothing to do with probability. And it has nothing to do with so when you say this is, of course, yeah, it averages out noise, but you don't have a real noise model. So if what you are saying should make sense from a probabilistic perspective, then you would have to define what your spatial noise is in terms of a probability distribution, and you would have to fit that based on the data. This is not what this is all about. This is just about, there is some data, it looks like this. You do a spatial weighting by using a Gaussian filter window, and then the data gets smoother. So the problem is, yeah.
Blurring the data? Is it blurring the data?
It's blurring the data. It's like you put a blurring or a Gaussian filter on in Photoshop. Just the same thing. There's no relationship to probability theory, and if you say it minimizes the noise, this implies that, for example, you have a model in your head that says that a little voxel here that is on its own active, this must be noise. But this then must be derived based on some probability model, which wherever you read that was not the case, and is most of the time not the case. Yeah. Okay. So if you want, so the maybe going on there. So the spatial model, there is actually a spatial model that also models spatial noise, and this is random field theory, which is a spatial model, and the model of the noise is that it has a specific, namely Gaussian process, and then a statistical random field a covariance function. But this is a whole, like I said, this is a whole semester course to go into that, and we first need to talk about GLM anyway. Yeah? Good. So here, just see it as a smoothing. Smoothing just makes data smooth. That's what it does. So then to finish the whole thing, that's fine. Anatomical normalization. What this refers to is getting the brain of a single participant into some common space, so that you can compare the activations of different participants and maybe even do a group analysis where you have a voxel that refers to the same brain area in different participants. And anatomical normalization is always done when you do group analysis, and I think the common form of data analysis, if you're not doing for example, what was this thing? Cortex layer. If you don't do layer-specific imaging, like we talked about the other day, you do some form of group imaging. And to this end, it's first important to recall that the brain has certain axes, namely a z-axis, top to bottom, a right-left axis, which is usually x, and a front to back, which is the y-axis. And a helpful thing to establish a common space for brains is that one has some landmarks that somehow define certain things. Now, this actually shows already how essentially all common brain spaces are defined. The 0 point in a brain space is always the anterior commissure, and the XY plane is arranged in the plane of the line connecting the anterior commissure and the posterior commissure. So the anterior and posterior commissure are just fiber bundles that collect the left and the right hemisphere, like the corpus callosum, but one can see them quite easily in the brain and also on T1 images. So this is something that one needs to recall, that there are brain axes and there are anterior and posterior commissure. And based on that, one can then talk about different aspects of the brain and different orientations. So this view of the brain is called a coronal view. Here you can see the X and Y axis and the superior and inferior. You have axial representations, anterior, posterior, left and right, and the sagittal view where you see the superior and the posterior and the anterior. So these are just the axes of the brain as they are defined. Now, the problem is, even if you have these axes defined, if you want to do a group analysis, you still have the case that, of course, people are of different sizes and of different shapes, and this, of course, also applies to their brains. So if you want to, on one single image, represent the activity of an entire group of participants, you need to make sure that each point in this image that represents the entire group of participants somehow represents each individual participant in a nice way, or in a meaningful way. And this essentially means that you somehow want to do away with this inter-individual brain morphology differences if you're doing group analysis. And for anatomical normalization, there are essentially two. There's one space that is usually used, which is called the Talairach space, which not more into the Talairach space and MNI terms. There are two things around, namely Talairach space and MNI space, but they are closely related, and this is what I'm trying to explain now. So Talairach space is a normalized brain space, and this is its history. So originally Talairach space was proposed by this guy called Jean Talairach in 1967, I think at the MNI. And it essentially uses a Cartesian space, so just a common X, Y, and Z coordinate system, and a 3D proportional grid in this in this Cartesian space. And the Talairach space is based on a set of anatomical landmarks, namely an anterior commissure, posterior commissure, the midline sagittal plane, so that's in between your hemispheres, and then the exterior boundaries of the brain at each edge. And its origin, and this is important also for MNI coordinates, is that it's there where the anterior commissure, as I've shown on this other slide, intersects the sagittal plane. So how does it look? This is what it means. So Talairach space is defined as follows. So here you have the anterior commissure and the posterior commissure. This is the origin of the Talairach space. So this is the 0, 0, 0 point. And then Talairach space extends until the borders of the brain, and That's essentially it, and its midline axis is defined by this interhemispheric cleft. Yeah? So essentially you can think of putting just a rectangular box or cuboid or whatever you want to call it around the brain, and this is if you have an individual brain, it's completely defined by its origin and the edges of the brain. Now, why was that done, and why is that interesting? Because there's also something called the Telaira Atlas, which is a brain anatomy atlas, which does something like Simon Eickhoff implemented in the SPM anatomy toolbox, essentially without implementing it. So it is an atlas that describes the names of brain areas based on a single brain, and it has labels for brain areas in the sagittal, coronal, and axial sections. And this Telaira Atlas is based, where is it? Yeah, this is based on, of course, a single brain. So you have to think how this works. So you want to make an atlas of the brain. Okay, somebody has died. You take the brain, you cut it into sections, and then you label the areas based, for example, on histology, like we saw last week. And then, for example, you say this is Brodmann area this is Brodmann area this, and that, and so on. Now the problem is this is based on a single participant. And this single participant, of course, might have a different brain shape than people that you are currently investigating. Now, if you then want to figure out a label for a brain area in the participant that you're currently investigating, you somehow need to map your participant data brain to the brain that was used in this Telaira atlas. And for this, Telaira proposed a simple procedure to register any brain to the atlas. So basically, if you have your own brain, you need to define the anterior commissure, the posterior commissure, and then the Telaira space, and then you have these different boxes in Telaira space. So this box, this box, this box, this box. And then essentially you need to stretch each part a little bit in there to make it align with the Telaira brain. Now this was, of course, before computers. Once computers became available, you could, of course, do the stretching. I actually don't know how they did the stretching with the anatomical sections. Maybe they actually put them, I don't know. Not with, of course, the original Telaira, but with your own. But once you had imaging, you could, of course, normalize the data that you have, the MRI data, by stretching or sharing it into the size of the Telaira space sub boxes. And this you can essentially do based on templates. So you need a T1 image, and then you have your own image of a participant, and then you somehow need to morph your own image into this. And if you morph all of your own images based on your participants into the one that is MNI based, then of course all of them are kind of normalized the same way, because they are all normalized with respect to a specific image. So these MRI-based templates, they are, and this is how this whole thing is related. What happened there is people acquired 300, for example, for this MNI 305 template. People at the MNI, so the Montreal Neurological Institute, acquired 305 T1 images, and they were aligned to the Telaira atlas using landmark-based registration. So for each of these images, the images were morphed so that they align with the Telaira image. And then these T1 images, these aligned T1 images, they were averaged and then created this MNI 305 template. So MNI space and Talaiura space are actually the same thing, because the MNI space things were generated by aligning these 305 T1 images to the Talaiura image. And there's another template, the ICBM 152 template, which is a higher resolution than the MNI 355. So this shows actually the images. So this is the MNI 305 image that was created by these people, and now what we can do is we have our own T1 image from our participants, and we can use an algorithm to morph, to estimate the parameters of our participants to align with this image, and then apply these parameters to the data and hence resample it in such a way that it looks like that. That doesn't work anymore with only translation and rotation, of course, because you might have to also inflate or compress some brain so that it has the same size as this. So this is the SPM way of looking at the MNI 305, and this is the ICBM 152. There are more templates used in SPM. For example, what I prefer to do is actually directly align the EPI data to an EPI template instead of aligning T1 data to T1 template and then using a co-registration of EPI data and T1 to also get the EPI data into MNI space. One can do that directly using, for example, this SPM8 EPI template. How they were generated, like I just told you the story about these other ones, you can read here. That's interesting, and you learn something. I don't remember what's the story behind them, but essentially they are based on some EPI scans that they did and aligned to T1 images and so on, and in the end they had this EPI template. So what a lot of people do, as I briefly hinted at, is, this is what I'm looking for, is to actually use the T1 templates and T1 data from participants and align those, so basically to get the parameters to morph the participant-specific anatomy into the template. At the same time, they co-register the structural data, so the T1 data, and the EPI data. So they try to align the EPI data, which of course always looks a little bit crappy, with the T1 data. And then use the parameters of the T1 normalization with the EPI normalization. And then people do all sorts of things. So, and this is what is shown here. So what one can do, and what is called here one-step normalization, is you have an anatomical image, you align that with a T1 template, and you have morphed your specific participants' data into an MNI-spaced brain. And this is just simple and done. However, of course, this doesn't help you for fMRI data analysis because this is T1 data. If you want to do if you want to have all your fMRI data in one common space, you can take each participant's functional data and align it with the with the EPI template, which is in MNI space. And then you have put all of your functional data into EPI space. That's fine. That's how I do it most of the time. What you also can do, and this is what I briefly mentioned previously, is to align your functional data with your anatomical data on a single participant basis. Morph your anatomical data into the anatomical T1 MNI space. The reasoning here is that there's more information in the anatomical data, so that this morphing here is done better if you do it on based on the T1 anatomical data rather than on the EPI data. and then use the parameters that you estimate here, use these parameters to go from here to here to do the normalization of the functional data into MNI space. And you can even make it more complicated by, for example, so I think this is a T2 scan. So you can align your T2 scan with your T1 scan, have the T1 scan normalized to MNI space, and align your functional data with your T2 scan, and then take the parameters that go from here to here to here directly on the functional data and have your normalization based on this. So you can do all sorts of things, and I personally prefer this here, this functional. You have your functional data, you morph it into the MNI space by aligning it with the EPI template, and you're done. But I think I'm a little bit alone with that, so I think a lot of people prefer these more complex ways, although there is not really that much data that shows that this is really that much better. So there has been a paper recently which was about what? Was going a little bit in my direction, but then not quite. I think there was some, what was that, only anatomical data, whatever, I don't remember. So the thing is, there are these ways, and you can get completely lost in like using the parameters from this here and there, and of course makes the whole programming more complex. Sometimes I feel people just do it because it can be done, not because there's good reasons to do that. But the basic idea is that you morph an individual's brain into a standard space.
But doesn't the data get kind of like
distorted?
Inaccurate?
Yes.
The more stuff we do, the more of it?
Yeah. I mean, in the end, you just apply one transformation here. But definitely what it means is that the individual raw data is somehow morphed into something different. That's always the case, whether you do it simply in one step or in 3 steps. And this then always means that what you have on the group level representing your single participant is not really what the single participant is really like. So this normalization is never perfect in any sense, because in the end, and this is then where people start being interested in inter-individual differences, no 2 brains are alike. So you can force them to be alike, but then what you get is something that is interpolated and made up. Or you cannot do it. The question is, do you want to make statements in your research about humans or about Aline? I mean, you also saw that last week from this classification based on resting state in male versus female, which, one can do. I don't really know what the point of doing something like that is, but this is then the question goes into the same direction. It's like if you do this for males and females, put them into the same state, but are male and female brains different? And then you can start a whole debate and get very emotional, or you not get very emotional, or whatever. The whole thing is kind of, one can computationally do things. The question still is that reasonable? Does one want to do that? Do we want to find, do different people actually have the same brain areas so that it makes sense? Or does everybody have their own brain? And you cannot really compare different brain areas. But this is how usually things are done in fMRI research for group studies. And that's called anatomical normalization based on MNI templates. So that was everything I wanted to say about preprocessing. Now if you go into a lab, you can either do a year of preprocessing your data different ways, or, and this is what I would advise, is you do one preprocessing screen, you make sure that everything runs, and you use the defaults. That takes you, when you do it for the first time, maybe 2 or 3 weeks to have that implemented. So, and then you have the preprocessing, and then you can do actually the data analysis in terms of the statistical modeling. And then at one point you have figured out what kind of data analysis you actually want to do. And then you can maybe go back to your preprocessing. Of course, you want to do everything in script so that you don't do things manually again, and maybe change a little bit with the preprocessing and see how strongly the preprocessing affects your final result. Never do something like you do one preprocessing, get one result, and then you start fiddling with the preprocessing, and then you start fiddling with the statistical analysis. This often happens, and it delays everything, and it gets all the fun out of things. So look at preprocessing in a very pragmatic way. If you do the preprocessing differently, your final results will be different because you do a different analysis. So the important thing is that you do everything script-based so that it can be really be tracked, and that you, once you somehow think you have found your result of your study, that you, in a way, protect it a little bit in the sense that if you change the preprocessing a little bit, that not everything goes away, so that you're highly sought after statistical significant result, once you make the smoothing 0.5 millimeter less, goes away. And it was really just all, not all, but it was strongly determined by your specific preprocessing routine. But what I want to say, and this is also why I go over preprocessing quite quickly, I could also do a full course on computational anatomy. It's for the interpretation of fMRI studies. The preprocessing is not that important. The interpretation is completely determined by the statistical analysis that you do, whether you do a GLM analysis, a DCM analysis, maybe an MDPI analysis. This really affects the scientific meaning of your study. So if you do a little bit realignment more, a little bit realigning less, that doesn't change the claim and the story that you make about the brain afterwards. So this was preprocessing. Please look at it pragmatically, but this will depend on which lab you work in. So the big thing that is then left actually for to do is to talk about actually the data analysis. And as I said, we will go from now on, we will talk about this, because this is still the workhorse of fMRI, and also for things like computational fMRI plays an important role, and for just understanding statistics. In the summer term, we will talk about this. This you can forget, because that's old school, 90s, nobody's interested in that. This is not as great as it seems, and I will talk about it in a year. Yeah. So this actually then ends the first half of the fMRI course. The next half of the fMRI course is to go back to section 2 and really do section 2 now. And really do imaging. So from next week on, we will talk about, again, so that you know what we are talking about from next week on again, we will talk specifically, for example, about things like that. Yeah, so, but we will start with talking about what differential equations actually are. Good. Questions, preprocessing, anything? No? Good. Then let's stop here and see you next week with whole new courses, GLM and MRI. Goodbye.